simulate the solar cell, you can either do that with graphical interface, which we will do, or maybe in the future you might want to use your own scripts. Okay, so that's more of a graduate work, but you can, that also accepts scripts to define the junction, to define the certain points of the solar cell, like we will discuss. Okay, we'll just use the graphical interface and continue with the simulation. So we must be all here underneath the second part, and we're just going to run a few examples that were already embedded in the software here. So we're going to click on this thing that says example. We're going to call the examples. First, we're going to refresh our memory and to make sure that everything settles down, all that information, we're going to simulate a simple diode. So under no illumination. Okay, so select that. It's a crystalline silicon solar cell, but there is no light coming in. So it's just going to act like a normal PN junction diode. All right, once you select that, there's going to be 3 layers here. So let's make that 2. Because we won't be really caring too much about the 3rd layer here. And let's just quickly look into the definitions of the layers. So this first layer is 300 nanometers thick. So let's try to draw the layers. This is the first layer. That is 300 nanometers. And what's the type? That's the second information. It's N-type. C, it's not just N-type, but it is heavily doped. So what did we say about the heavily doped notation? We would put a plus, right? Because by experience, I know that this is really very, very highly doped. Remember, I talked about the saturation point at some point during the discussions. It's like around 10 to the 20 level. So this is quite close to that. And the band gap is modified accordingly. So it's a little different than the usual 1.1 electron volts of the silicon too. But it's not really far away either. Okay. Several of these are not super important for us, but okay, so let's not go into the discussion of those. Yeah, that will be good enough for us for the diode. All right, now let's switch to the second layer here. And let's try to draw it in a scale. So this is C in terms of micrometers, almost 200 micrometers long. So let me change the color. This is really long. This is this time, of course, we have the N-type, so we will have the P-type. And see, it's not that heavily doped, so it's only 10 to the 16, the concentration of the dopant. All right, so what did we have for the P-type? So we have the holes here, right? And we have the electrons. These were what we called the majority of the population. So they are the majority carriers. We still have some electrons here as well, but they're tiny. Their concentration is tiny. And as for here, we have the electrons as the majority carriers. Okay. And so we are kind of ready to actually do the simulation. So once we go up here, we define the layers. We didn't really play a lot with the layers definitions. They were already there. Now, if you go to the absorption, this is what we will use for the case when we illuminate the diode. Okay, we're not there yet. And we will also make use of but these are again, they have to do with the contacts. We won't be making use of these a lot. Now, coming to the simulation, it's now under dark, and let's change this to be from -1, because I want you to see the reverse bias condition too. Okay, so we're going to scan from -1 volts. So what are we doing? We are tying this up. This is not a solar cell yet. We're tying this up to a power supply, a battery. And remember, what would be the polarization? Of course, during the scan, it's going to change. So once it's -1, okay. So ideally, remember, we would like to put the plus sign, what we said, the anode side to be attached to the p-type, and the other side would be the n-type. So I'm hoping it didn't kick me out. 1 second. Okay. All right. Yeah, we're still here. Good. All right. So we are ready to simulate. So we can hit the simulate button. We will see the effect of this first, the equilibrium condition, when there is no battery, but then we will see the effect when we have the battery. Okay, while it's doing that, let me share my other screen with you, because I would like to remind you what the expectation would be. Okay, so hopefully you can see the slide here now. So what was our expectation? So we had the N and P sides. So this is the forward bias. So remember, we had the P-type, oops, the P-type here, and the N-type here. We would have the band bending condition. Maybe we can first talk about the other slides. Yes. Right. So under equilibrium conditions, this was our situation. We had the P-type here and the N-type here. How do I know that? Because the Fermi level, again, is close to the valence band for the P-type, and the holes are the majority carriers here for the P-type. As for the N-type, the Fermi level is close to the conduction band, and this would be the equilibrium condition. What was prohibiting the current? Well, these electrons that are the majority carriers on the N-type would have to hop over this naturally occurring barrier, right? How did that barrier occur? Just let me refresh your memory. We had these these electrons here on the N-type, and for the P-type, we had the holes. Once we put them together, they kind of diffused very, very quickly to each other side, but that's like a very transient action. Later on, once they are gone, okay, once they are gone, they left behind the uncompensated ionized dopants. What were they? Well, every hole was compensated by the boron, right? So if we think of holes as the anti-electrons, so they have like a positive charge, so that was being compensated by the negatively charged boron ions in the crystal. So boron would be embedded, so we would have these guys left. Once the charge carriers are all depleted in this depletion region. And very similarly, we had the electrons compensating the phosphorus, and they would have a plus because once their electron has gone away, they would have they would be ionized and they would become a plus charge ion. So this, when we put the PN junction together, created, as you can see, a capacitor, kind of parallel plate capacitor with plus charges here, negative charges here. So as soon as you see that, remember the electric field formation, okay? And I emphasized yesterday that the electrons as negative charge particles would see these ions here. They are really troublesome ions for the electron, the poor electron, because whenever the electron wants to jump to this side to conduct, right? That's how the conduction will happen. The electron will be transferred from this side to the other side. It would be repelled back. It will say, no, I don't want you here. These ions would be stopping. Likewise, the holes would be stopped as positively charged particles, quasi-particles. They would be stopped by these ions here. So there would be no conduction in the end. And that would be the reason of this barrier for the electron. The probability of conduction would be proportional, would be exponentially decaying while we're increasing this potential barrier. Okay, so far so good. And then that's what we did. We decreased the potential by applying an outside potential to fight back against this barrier. So we put a battery and we lowered down this potential barrier. So we enabled this hopping for the electrons. So what happened is electrons who were majority carriers here, they hop to this other side and they become the minority carriers. And it's actually in the diode, this minority carrier action into the other side that will create us the current. This will be the different thing for the solar cells, as you might remember and as we will again see. All right, now let's get back to the simulation. So I am gonna share my other screen. Okay, so first, this is refreshing us about the doping concentration. So I hope the simulation also ended on your side. So this is just showing us the dopant concentration, and it might be actually good to set this to 0 because we'd like to see things under equilibrium first. Okay, so just use this slide bar here and put things to 0. Okay, so what do I see? I see the acceptor concentration all around. Why? Because the N site was very thin, right? I just talked about it. So we are gonna zoom into this region here with our mouse and just draw a rectangle and then you will see that, okay, there we go. This is of course logarithmic scale. So this is a better view. So we have the donor concentration going up to 10 to the 19 here, whereas the acceptors are 10 to the 16 here, as you can see. Okay.
Can you show us how to do that part again?
Say that again, sorry.
No, he can't hear you. If you have a, can you hear? Can you hear?
Yes, when you're closer to the computer or the microphone, I can hear you better. Yes. Can you repeat that?
Mics on your desk are not working. The only mic we really know works is the one you're on the computer. Sorry.
No, I was just asking, can you show us how to do that part again?
Sure, of course, of course. So if you want to zoom out, so you will use the right click. So right click will take you back. So this is where we started, okay? So what I'm gonna do is click on your left click and it's gonna say zoom number 1, for example. And then I'm drawing this rectangle here and then just releasing the left click. And then I'm gonna do that again because I'm not seeing it in the full scale. So I'm gonna draw another rectangle like that, maybe even another one, because why am I drawing all these rectangles? Because look, the N side is very thin. The reason will be apparent when we use the solar cell mode. This is still the PN junction, a simple PN junction. So I hope this solved the problem on your end. Now the donor concentration is 10 to the 19, as you can see here. And the acceptor concentration is here. So the junction is expected to be here when these two meet. Okay. So now, after visualizing this, this is something we already put into the simulation tool. So this is not really a result. We already have put that in. We are going to be looking into the energy band diagram. So let's choose energy band diagram, because I would like to emphasize that any solid state device cannot be understood, or will be best understood, I should say, with the presence of band diagrams rather than mathematics, I would say. So once you select energy band diagrams, it's gonna bring you this. So again, what do I see? I simply just see the p side. How do I know that? Because this is again the conduction band of the p side. This is the Fermi level. Okay, so it's saying quasi Fermi level because I forgot to put this to 0. Okay. Actually, I'm kind of shorting that there. Yeah. Okay, so now we have the valence band here. The Fermi level is very close to the valence band, as you can see. So that's just the p side. What I'm gonna do is I will zoom into this side again, just like I did before, to look into the band banding. So just like similarly what I did last time. So even if you make mistakes like I did, they're happy mistakes, happy accidents. So that's all fine. So let's try to zoom into this region. I need to zoom out, and if you make a mistake, just zoom out with your right click and then try it again. Okay, so this is good. Okay, right. Now we're able to see the band banding much clearer. So I have the P side here, and I have the N side here, and look, the Fermi level is even embedded to the conduction band. So this is what I meant by really heavily doped side. The likelihood of finding an electron is very, very high on this side, right? So that showed us the water level. If you would like to picture it that way, this is showing us in a way the water level of finding, or the water sea level of the electron. So it's really, really here. On the other side, it's only here. So it's not as likely as the other side by far. This is really drastically different. Okay. Now, as the next thing, let's look at the carrier concentration. Okay. So once you select carrier concentration, it's gonna show us what? The holes, of course. Where? Inside the P side. So let's draw that again just to make it visual for us while we're examining. So this was the large P side, and the other one was the small N side. So I will have holes here all the way and electrons here. So there's going to be a depletion region here, but then I will assume that these are still in a way like quasi-neutral. Okay, so I will have holes here, and that's their concentration. I told you it's not depleted of electrons, so I still have some electrons here as well. Okay, so what's the interest? Well, the interest is to put this first to 0. Okay, and then zoom in again to the PN junction. So doing the same thing. All right. And on the other side, of course, I have electrons. So how do I know that I have created the depletion region? Because see, they are getting depleted. The charge carriers are getting really low within this region here. Okay, but now let's try to understand the effect of the voltage, because I told you that in the diode case, the simple diode case, with the applied battery, I will, if I put it in the right condition, the right polarization, like plus and minus, plus to the P side, and side gets the negative side, then we would encourage the electrons basically to hop to the other side and start conducting. So that was how we were doing it. So basically what we're gonna hopefully see is this concentration will rise up, and the electrons will be able to penetrate to the P side. So let's see what will happen. Now this is the 0 voltage. You can say options here, and you can click to be a little faster because it has a lot of voltage values there. It's all up to you. And then you can click this guy here. See, like I told you, the electrons are jumping to the other side. How? Well, with the applied voltage, especially after like 0.7 volts, as you can see here, the concentration has been really elevated. Now, the electrons are on the other side, but the level between the concentration of holes and the electrons are really not that high either. So we are able to encourage the electrons to jump to the other side. This is all thanks to the plus voltage that I'm giving. So you would expect that we would obtain a current out of this, and it's exponentially going to increase because I have an exponentially increasing number of charge carriers on this side. Okay, now let's do the reverse. So we will go playing with the scroll bar. We will not click this, but we'll go to the other side. So this time the polarization will be different. So let's think about that. The polarization will be different. So first, actually, let's try to visualize maybe the energy band diagrams. So switching back to the energy band diagrams. Now, I'm going to scroll to the other side, to the negative side. What would we expect? As we emphasized, if we do that, we would build up more and more electric field inside. So that would make sure that we would have a larger barrier here. So the barrier will increase. So let's see. For the positive side, I know that the barrier will decrease. For the negative application, the barrier will start really increasing. So if I click, yeah, it zooms out, so you can see the barrier, and then you can zoom in again to see. So as I do that, it's really becoming really, really high. Okay, so at this point, let's look. So I have majority carriers as holes here, right? But there is a barrier for the holes to go to the other side here. So since it's actually the opposite charge, so for them, they're seeing the exact, very similar barrier that they were seeing here. So even though it seems that they have to go down, it's actually the other way around because these are positively charged particles. So the energy bands, if this is a barrier for the electron, in this case, like going up like this, it's going to be a barrier for the hole to jump to the other side too. So for that, in that case, while I'm increasing this barrier, I'm actually trying to drive the poor little electrons that are here. How? Because I have created a large electric field. I have now the ionized charges left. So I have these charges left, and I'm also making sure that I'm applying more positive here and more negative there. So these poor electrons, whatever we have, will try to hop to the other side. But it's actually like falling down the waterfall. It doesn't really matter how much the barrier or the waterfall is, the height of the waterfall is. It's actually more about the number of electrons that are sitting here that will determine the new current. So this will be all limited because I don't have too much of population of electrons on this side. So it will not be very much dependent on the applied voltage anymore, because that's just increasing the barriers, increasing the waterfall, but it's not really a critical factor for my current. So that is why I'm emphasizing that energy band diagrams already giving us a lot of insight before looking at the IV curves, which we will examine in a bit. Those are the current and the voltage curves. So now let's look at the carrier concentration. We will go to the other side. See, I mean, we're trying to get these poor electrons on this side, okay? And we're trying to deplete them all and trying to, under the influence of the electric field, we're trying to drive them in the opposite direction. Okay, and that's really not, that doesn't matter a lot, like based on the voltage. Okay. All right. So now we are ready to look into the next thing, the IV characteristics. That's the last thing we maybe we can look at one more thing. Let me see. Excess carrier, optical generator. No, this doesn't have the charge distribution. Yeah. So let's look at the IV characteristic right now. And this is what we end up with. So this is the 0 point, okay? So all this part here is what we call the reverse bias, where we would increase the waterfall height, but it doesn't depend on how much the water height is. It depends on the population of the electrons. So that is kind of almost independent of the applied voltage. So this is voltage axis that you're applying. This is the current that you're extracting. In a way, you can think of it like the electrons that are going around the whole system and creating the or completing the whole current. So we have the battery here, and we will have a current that's flowing in based on the, of course, the battery polarization. It will depend the position, but this has to do with the electrons that are continuously going in both directions. Okay. So as for the positive bias, on the other hand, like I said, there's going to be an exponential increase because we're decreasing that barrier, and the electrons will have a better likelihood. So after a while, it will be really very much easier for the electrons. So that's the threshold voltage for the diode. And if you want to integrate a diode into your system, for example, that's what I was doing when I was an undergraduate too. I was putting these diodes into my electric system, electronic design. And when I go to purchase a diode from the manufacturer, I was just looking for, at that point, like the threshold voltage, what is going to be the point where they will start conducting. So that was the most critical thing for me when I was looking from a system perspective. So this is more or less that voltage that when it will start to conduct. Okay. All good. So this is the basic diode. I hope I was able to reinforce you the diode basics. Now we will continue with the solar cell. So going back to the first simulation option, and then we will say again the parameter list. And in this case, we will select the silicon crystalline silicon solar cell now in light. Okay. You're all with me? Okay. Now we will really make use of this third layer, and I'll explain that. But if we look at the parameters here for layers, we see that the layer thickness is 0.3 micrometers. It's almost the same. I mean, not almost. It's identical. The same diode that we just looked into. Okay. And the other one is the P-type, the large P-type. That's also the same. And now we have another layer at the bottom. So if we were to draw it, we would have 3 layers. We would have a thin layer here, another layer here. So this would be the N plus region, the P region. Now the third layer is also P-type. It's 0.8 micrometers thick. So it's intermediate. It's not as thin as the N plus, not as thick as this, of course, the P. P is the dominant. And it's also very heavily doped. So 2 times 10 to the 18. Okay, now let's run this simulation just as it is. Okay, and then now this absorption file will be used because this time it's going to be, the light will be absorbed. We're not going to touch that part. Okay. So when we come to here, this portion is here to actually give you a standard for the incoming light source. So this will make sure that everyone doing simulation or everyone doing experiments all around the world will use the same input power from the calibrated source, the light power. And we will not really touch anything. We will later on change a couple of things here, but we will just hit the simulate button. And as it's doing that, let me share my other screen again. Because let's remember how the solar cells work from yesterday. Yeah. So in this case, the idea was we would create these charged particles. So like we would create the electron and hole pairs with thanks to the light. Oops. For some reason, I lost the. Okay. Yeah, when the light's energy is enough, higher than the band gap energy of the semiconductor, created charged particles. In this case, this would be again the p-type portion, and we would have the n-type, of course. The created electron now as the minority carrier on this side, we would try to drive it thanks to this, again, the drift influence of the p-n junction. That's why we're using the solar cell. We're kind of trying to understand, like trying to isolate these two into their own region. So we will say, okay, I have an electron here. The electrons need to go to this side, okay? So that's going to be the new idea. Instead of trying to send the electrons from this side to the other side over the barrier, that's what we just did for the simple diode, we will now force the electrons to go to their own side, the N side. Okay, so that's exactly why the illumination current will flow in the reverse direction than the normal PN junction diodes, because we are forcing the electrons to the other side. This will make sure that we will have a nice hole and electron nicely separated from each other. Okay. After I hit the simulation thing, it has a tendency to kick me out. But yes, now we have solved it. And it's going to show us this as the simulation number 2. So if you use the scroll bar, it's going to show the one that we previously worked on. That is the simple PN junction diode. If we come here, this is the solar cell right now under illumination. Okay, everything is the same. We just edit this layer. So if you zoom into this part, you will notice that I have now this additional P plus layer, like we said, right? And the acceptor concentration would be higher. What will be the implication of this? There will be a banding. So if we select now in this new simulation, energy band diagrams. Let's select energy band diagrams. And once we do this, we will realize that there's going to be another band bending here. Because here, okay, it says quasi, but let's make it simpler. The whole, the Fermi level here will be closer to the valence band because this side is heavierly doped than the other side, the previous P side. Okay, so this is my P plus side. my pen is creating problems here. This is the P side. So to equilibrate again the Fermi level between the two, I would have to again bend these energy bands. So we'll come to the importance of this in a bit. Now I'm zooming out. Let's look at this time the IV characteristics. Again, gave me the same thing. So I am hoping it gave you the right result. Let me just terminate this one and I will, because it doesn't conveniently show me the whole thing. So I'm just gonna open it again. For some reason, sometimes it's not showing the whole picture. So I'm just going to the same example, not changing anything, just hitting simulate. And then looking at the IV. Yes, this is what I was actually looking for, finally. So we read an IV current. This is just a flipped version. So what did we say about the diode current? So this is my I, the current. This is my voltage. As I'm increasing so this is the reverse part, it doesn't really conduct that much. And as soon as it goes to the positive side, it starts conducting. For the illuminated diode, okay, in this case, this is just the mirror symmetry. What I mean is, it's actually gonna, so once I send the light, okay, it's gonna start conducting in the opposite way. So it will have an illumination current that's being conducted in the opposite way. So you can think of it simply as a superposition. So we will decrease this overall graph. It's a simple mathematical problem. Just lower it down by an amount of IL. Okay, it's not as simple as that, of course, but just bear with me. We're trying to do that. So I tried to draw it, but I hope I was successful. So this part actually now has been just flipped to this part. So that's why it's showing us like that. You may ask, why is it doing it? Just for convenience, actually, because people don't like to work in this negative quadrant, okay? They just flip it to the other side, but actually, this is what we're observing. Now, I told you a couple of things, that there would be an important definition, the efficiency of the solar cell, which would be given as okay, I'm trying to draw the best rectangle I could get. That would involve the two areas. That area and roughly like maybe a little less, but this area. So the efficiency would be correlated to the filling factor, okay, which would come from the division of these two areas. Okay, so the big red area and the smaller blue area. Okay. And I would like to remind you that the efficiencies of the solar cells, simple solar cells, are like in the range of 20 something percent. All right, now we will do the following. To understand the importance of that, the third layer, we will go back to our parameter list. And this time, if you come to the third layer, let's try to kill that by saying I will have only two layers. Let's try if it will work this way. Fine. Okay, so I killed the third layer by just saying I have only two layers. Number of layers is 2. And let's hit the simulate button one more time. Okay. All right, now let's look at the energy band diagrams. Well, now in this case, I would not see that banding here. So see, I don't have that additional layer. So the energy band diagrams are flat because I don't have that layer anymore here, simply. So now if I go to the IV characteristics, it's going to give me this. So this is the new IV plot, and let's try to compare this plot with the previous plot that we had. Okay, I hope you can see the difference. So this is the new plot we just created without the third layer. This is the plot we gained with the third layer. This is the previous simulation we just did. So of course, this second one, as you can see, will outweigh the performance of the new one. So that's why actually we are putting the third layer, because we'd like to increase the efficiency, and I am increasing the efficiency. Just let's look at the current that we can flow to through the solar cell. The solar cell is right now running 39.4 milliamps. So 39.4 milliamps per centimeter square. This is with that third layer. Without the third layer, I am running 38. So you can see we have elevated the short circuit current. And we also increased the open circuit voltage too. So these are the open circuit and the short circuit currents. So these are the crossing points of the X and Y axis, basically. These are the two important parameters because my solar cell efficiency is all related to the multiplication of these two. So it's 0.6 here. The higher, the better. So when I put the barrier, the new layer, it's going to jump up to 0.62. And the current also jumps up too. See? So this is immediately showing us how we can increase the performance of the solar cell, but we can also compare it by looking into one more thing. So let's try to do the following. Go to the parameter list, and this time we will say in the simulations, let's activate the quantum efficiency. This is going to show us how well the solar cell will absorb the light, okay, in a way. So just turn this on and simulate. In the meantime, let me show you what's going on. What's the difference between these two simulations? Okay, so we're here. And like I told you, this is what's happening. So this is just a simple diode. Okay, I'm not sharing the right screen. Let me share the right screen. Yeah. So this is the simple diode that I have. What I'm doing is I am illuminating with the light, and it just lowers down the whole graph, because now we're creating the charge carriers, meaning that we have a current that we are creating too. And as I'm illuminating with more light, it goes down even more. That's the idea. And then we just flip it up. That's exactly what we have seen here. Okay. So how about that third layer? What's the importance of the third layer? Okay, here's the importance. We have to remember the recombination. Okay, we're creating these electron hole pairs. Let's see. I showed you this earlier yesterday too. So the light comes in. Let's see one more. Light comes in and it creates an electron hole pair. So that's good. And this electron now can make to the N side. So we created another electron hole pair, but see what happened? this guy caught up with the hole, so they recombine. We created another electron hole pair, but they recombine again. So especially they like to recombine at the end here. So that is why we try to avoid that scenario. So this is what we're doing actually. We have these electrons in the p side. So whenever we have electrons in the p side, we would like to make sure that they don't reach the bottom layer here, which is the metal solar cell junction, the place where they meet, okay? There are too many defect sites here, lots of defects like we covered earlier. So that creates the opportunity for the electrons to be lost. See, they're disappearing. Once they're created, they have to go to the other side, the N side. They should not come down here. To make sure that that is happening, we are basically adding that additional layer. And we are saying to the electrons, okay, let's add that layer. We're saying that, okay, we just doped this side. We added an additional barrier there. So it's no longer like this. And it doesn't just meet with your electrode here, the metal. But in terms of the energy band diagrams, we have a little bit of another barrier that is waiting right now for the electrons, okay? So if they happen to somehow go in the reverse direction, get lost, they will be they will see this barrier and they will not be able to recombine and get lost, completely being annihilated here. So I can make use of these electrons if I can recapture them too. And that's what we just have seen here. So let's go back to the simulation one more time. Okay. Now this time we will look at what we call the quantum efficiency. Okay, so if we zoom into this part, this is actually showing us how well the solar cell is absorbing, is making use of the incoming light and transforming it with respect to the wavelength of the incoming lights. So this is the wavelength, okay? And this is the efficiency, as you can see. So efficiency with respect to wavelength, all that light comes in, and this is the point around here. This is the point where the band gap of the silicon, our solar cell, ends. Okay. Beyond this wavelength, so this is what's happening. I have the band gap, right? And I have the incoming light. If the light's energy is higher or equal, then the band gap, I will be able to excite the electron and get the conduction. The solar cell will be facilitated. But here, the wavelength is increasing. That means that my electron energy is decreasing, because I would like to remind you, the energy of the photon is related with the Planck constant times nu, the frequency. Frequency is shown to be divided by c, the speed of light divided by wavelength. So if the wavelength of light is higher, its energy is lower. They're inversely proportional. So what will happen is my light source will not have enough energy to actually excite these electrons up to the higher energy level. Okay, its energy will not be sufficient enough. So that's why I'm not able to excite anything here. I'm not able to convert anything into electrical energy because of the wavelengths here. So this is the situation with the two-layer case. Now going back, we will do the same, but for the added layer. We will increase this to 3, and the third layer will hopefully pop up with the same information. And now we will simulate that again one more time. we'll try to compare and contrast the quantum efficiencies, how well the light is being absorbed. So what I'm trying to see is if I change the new share. Okay. Okay. So this is our case, exactly like our case. So we have the N plus side and we have the P side. The light is coming in and it's exciting these charge carriers, as you can see here. We will try to make use of this wavelength of light. But this wavelength of light, while it's getting in from the sun, the longer wavelengths will be able to penetrate to the deeper parts of the solar cell. So they will go into the deeper parts. That's a problem, as you can see. Why? Because if the electron hole pair is created here, their electron is very close to the metal side again, right? So I would like to prohibit that meeting center for the electrons, and I would like to encourage them to go to the other side. This is only true for the longer wavelength electrons. The shorter wavelength lights, I should say, not electrons, will be created here. So depending on the wavelength of the light that is coming in, their creation centers will be different. So the short wavelengths will be generally creating the hole pairs like in here. The longer wavelengths will create them here. So let's see what we're making use of how well we're making use of those longer wavelengths. Okay, so what do I observe between the two simulations? So when I have two layers, so these are the longer wavelengths. Let's zoom into the graph completely. Okay. So these are the longer wavelengths. The tail here is showing us the longer wavelength portion. This is the case for 2 layers, and this is the case for 3 layers. The 3-layer case is, of course, enabling us to convert the electricity much more efficiently. We are able to capture the longer wavelength electrons as well. Whereas for the 2 layers, I can't guide them well. They recombine. All right. So that concludes our solar cell discussion. And let's continue with the thermal oxidation. If you like, we can give a 10-minute break in between so we can continue right after. Does that sound good? Okay. All right. Let's give a 10-minute break and let's meet around 10:25.